Okay. Good afternoon, fellow researchers and chairpersons of the conference. My name is Christos Michail. I'm an associate professor in the Department of Biomedical Engineering of the University of West Attica, Greece. And this work was conducted by the members of our laboratory. You already referred to the title. So let's get started. The presentation is shown, okay? You can see the presentation?
Yes, we can see the presentation.
Okay, thank you. Okay, thank you. So this work deals with scintillator detectors. Scintillators are materials that used to convert radiation upon excitation from X-rays or ultraviolet radiation. So they have a lot of applications, from medical imaging, that is my discipline, up to applications for Earth environments, non-destructive testing, etc. Their performance is strongly affected by external parameters such as temperature and radiation, of course. So we have to monitor the effect of these parameters in order to select the optimum detector every time for the application that we need to construct. The aim of it's of course of worth to examine the influence of temperature on the luminescence output of single crystal scintillators. In this study, we examined three materials. All three materials are co-doped with cerium, and they are commercially available and applied to various applications. In medicine, we have used them in positron emission tomography scanners. The first material contains lutetium as a base material. It's the lutetium oxyorthosilicate. It is a very effective material with high luminescence efficiency, high light yield, but it is very expensive. Lutetium is very expensive, and also lutetium contains intrinsic radioactivity. This is a drawback for a system. So researchers developed further this material by adding yttrium to the mixture, and of course reducing the ratio of lutetium. The resultant material, the lutetium-yttrium oxyorthosilicate, has similar internal properties with the initial material and is a little bit cheaper. This is, of course, crucial for the industry. Also, it has a little bit lower luminescence efficiency than the former material. The third material has gadolinium as a base. It's called gadolinium orthosilicate, and is much cheaper than both the other two materials, and have lower luminescence efficiency, much lower than the other two. However, it is used in cost-effective applications. The aim of this study was to examine the luminescence efficiency of these three materials upon X-ray radiation, and of course with various temperatures. In the first table, we can see the internal properties of these three scintillators. We can see that the two oxyorthosilicates, the lutetium and the lutetium-yttrium, has similar density and effective atomic numbers. Also, their decay time is in the same region, as we can see here. However, the addition of yttrium in the mixture results in a little bit lower light yield comparing to the initial material. Furthermore, their energy resolution is in the same range. They both melt at similar temperatures. They have equal hardness, and they both emit light in the same wavelengths. The third, the cheaper material, the gadolinium-based material, has lower density and effective atomic number. The decay time is in the same region as the other two. However, as we can see, it emits much lower light than the other two. The light yield is much lower. It has worse energy resolution compared to the other two materials. It melts at lower temperatures. The hardness is almost the same value with the other two, and emits in the same wavelengths almost. All three materials are, of course, non-hygroscopic for these applications. In our experiments, the crystals, the scintillator crystals, have polished surfaces. All surfaces are polished and have equal dimensions for comparison purposes. The dimensions are 10 by 10 by 10 millimeters. And for the experiments, we wrap the crystals with Teflon tape, all surfaces except from one, in order to allow the produced light upon excitation to escape from the material. A thermocouple is adapted every time to the crystal surface in order to monitor the temperature on the crystal surface, and then the sample is placed in the input port of an integrating sphere. All samples are irradiated with an X-ray tube. The beam of the tube is filtered by a 2-centimeter aluminum filter in order to simulate the beam hardening by the human chest. Afterwards, the produced signal by the crystal is fed to a photomultiplier tube, to the photocathode. And then the signal from the photomultiplier tube is fed to an electrometer. The signal then is digitized and transferred to a computer. So with this procedure, we have measured the produced voltages from the crystal upon irradiation. The voltage then is converted to the emitted light energy flux of the crystal. Also, we measure the incident radiation on the surface of the crystal by placing a calibrated digital dosimeter, as we can see here. And we have also this reading. So by dividing the light energy flux with the X-ray radiation, we conclude to the absolute luminescence efficiency, which describes the performance of every scintillator, and with this measure we can compare their relative performance. The units can be seen here, and they are expressed in efficiency units. Now we can pass to the results section. We can see three graphs showing the relative the voltages, the produced voltages, with exposure time and temperature. The exposure time for all irradiations was set to 1 second, and as we can see from the graphs, after the 1 second, the signal stops. The crystal with the higher voltage values is the pure lutetium crystal, the lutetium oxyorthosilicate, as we can see, and the produced voltages ranges from 0.43 to 0.9 volts. The second most powerful scintillator is the Lutetium-Yttrium scintillator, and we can see that the voltages, the produced voltages range from 0.21 to 0.65 volts. The third crystal is the cheap gadolinium-based crystal with produced voltages from 0.24 to 0.34. A first thing to notice from these graphs is that both the oxyorthosilicates, the lutetium and the lutetium-yttrium, has great variation in the produced voltages with temperature. This means that its signal reduces a lot with increasing temperature. This is not the case for the gadolinium crystal. We can see that the reduction in the produced voltages is very small. This crystal appears to be very robust to increasing temperatures. And also we can see that the produced voltages in this cheap crystal after some temperatures is higher than the more expensive lutetium-yttrium crystal. This is an interesting finding. In the next slide, we can see a comparative analysis of the three crystals. We can see that the lutetium and lutetium-yttrium crystals has a similar signal drop-off with increasing temperature. And we can see that in these two crystals, we have a signal reduction of more than 50% and up to almost 70%. This is a very big reduction for a detector. On the other hand, the cheaper detector, the gadolinium-based detector, appear to be robust in higher temperatures, and we can see only a 25% reduction in the signal of this detector. Also, we can see that after about 88 degrees, the signal produced by the gadolinium detector is higher than the lutetium-yttrium detector, which is much higher and has a higher light yield in lower temperatures. At even higher temperatures, the signal of the gadolinium detector approaches the signal from the pure lutetium detector. This is also an interesting finding. And finally, we can see this luminescence efficiency results in table 2. In the lower temperature range, the pure lutetium crystal dominates. It is followed by the lutetium-yttrium crystal, and the lower values appear for the gadolinium crystal. However, in higher temperatures, we can see that the gadolinium crystal shows higher luminescence efficiency values than the lutetium-yttrium. And at even higher, we can see that it even approaches the pure lutetium crystal, which is the most expensive of the three crystals that we examined. So, as a conclusion, we can say that in this study, 3 cerium-doped crystals were examined. The two oxyorthosilicates with lutetium and lutetium-yttrium appeared with a big reduction in their luminescence efficiencies, whereas the much cheaper gadolinium crystal appeared to be robust with increasing temperature and with even higher luminescence efficiency values than the lutetium-yttrium. This is of importance when we need to construct a cost-effective device, imaging device that will be used in higher temperatures. Some references, and thank you for your patience. Any questions?